Figure to bias the MOSFET amplifier of figure 7.3 at point Q, for which V over drive is equal to 0.2 voltage and VDS is equal to 1 voltage. Find the required value of RD when VDD is equal to 5 voltage, VT is equal to 0.5 voltage and Kn is equal to 10 milliampere per voltage square. Also specify the coordinates of the VTC endpoint B. What is the small signal voltage gain of this amplifier? Assuming linear operation, what is the maximum allowable negative signal swing at the output? What is the corresponding peak input signal? Okay, the first part is asking find the RD value, that is basically this. So in order to find the RD value, we can also create the current equation. This current ID here should be, if you put the equation for it, this current ID should be this voltage minus this voltage right here, that is VDS, divided by the resistor in between, that is RD. And here we are interested in finding the RD value, so we have to just switch this equation. So this is going to become RD is equivalent to VDD minus VDS over ID. Now here the thing is, do we know all the values to solve this problem? Like do we know VDD? That is, we have the VDS. Okay, let me see. Okay, here we have VDD as well. So VDD is available. Let me take a note of it. VDD is equal to 5 voltage, and then VDS, that is also available, that is 1 voltage. And the only unavailable thing is current. Now to find out current, we can use this equation. Okay, current is given by ID current, that is equal to half Kn V over drive square. Okay, and we have Kn provided, that is 10 milliampere per voltage square. So let's put that one here. Kn is 10 milliampere, so milli 10 to the power minus 3, and then V over drive also provided, that is 0.2 square, and solve for the current. And if you calculate this one, you're gonna end up getting 0.2 milliampere. Okay, because this one becomes 0.04, that one divided by 2, 0.2, and then this milli comes into play. Okay, so you finally end up getting ID to be 0.2 milliampere. Now you can plug in this equation. Okay, let me just plug it here. So VDD is 5 and then VDS is 1, and then we just find out this ID current to be 0.2. So that is like 4 divided by 0.2, and this is milli. So that's going to make this one a resistor into kilo. So 4 divided by 0.2 milli is going to be 20 kilo ohm resistance. Okay, so now we have RD. That's the first part of the question. We did it. And the second part, let's see what else we have to find. Find the value of RD, and they have provided all the information. And the second part is also specify the coordinates of the VTAC endpoint B. Okay, here we have B. We have to find, okay, actually B is right here. We have to find the coordinates. Coordinate is basically, if you look at the x-axis, we have VGS, and the y-axis we have VDS. So we have to find both of them in order to express the coordinates. Okay. And this one is like, this one is changing from saturation to triode region. If you watch my previous videos, I used exact same graph, but it actually mentioning like each point what is happening to that region. So this B point in that one is basically it's changing from saturation to triode region. So at that point we can use particular equations. One of them is we can use this VDS that's equal to VDD minus, I'm just using the current equation, like here if you look at this, VDD minus VDS divided by the resistance in between should be equal to current. And you can rearrange this equation in terms of VDS. The only term we had to be careful is that ID. Instead of ID we can put an equation in the when it's changing from saturated to triode, we can use this particular equation, that is half Kn, that is for the current, half Kn VGS minus VT square. Okay, and this is just for the current, and also we have current multiplied by the resistance, that's the voltage here, because you see if you rearrange this one in terms of VDS, this current multiplied with IDRD, this ID expression is the one I written here, and the resistance I just put it along with this. Okay, now this is the equation we have to be careful about. So from this one, can we find anything? Because let's see what is known here. Here what we can do is we can flip this equation and solve it in terms of VGS minus VT, because that's going to help us to find a lot of things. Okay, and VDS is given already, there is 1 voltage. So we know that we are just interested in finding VGS and VDS in this particular region. Okay, but we can use this one in that equation, but let me double check. Yeah, so we have to find out VDS in that region as well, but the equation we have, we are going to apply this 1 voltage over there. Okay, let's do that. So if we rearrange this equation, this is going to become VGS. We are just looking at the region B, so I just put B for it, just to make sure that this is happening only in the B. And then VGS minus VT. If we rearrange this one and create an equation, that is going to be square root of 2Kn RD VDD plus 1 minus 1 divided by Kn times RD, and this minus 1 is outside of this square root. Okay, if I call this one as equation number 1, let's call this one as equation number 2. So from this one we can solve for the VGS minus VT, plug in all the values. Two times Kn value is 10 milliampere per voltage square, so 10 times 10 to the power minus 3, and then RD value we just calculated to be 20 kΩ resistance, so 20 times 10 to the power 3, and then VDD is provided in the question, that's 5 voltage, and then this is plus 1 and then minus 1, the whole thing divided by Kn times RD. Kn times RD, Kn is given by 10 milliampere per voltage, 10 milliampere per voltage square, so 10 times 10 to the power minus 3, and then RD is 20 kΩ resistance, 20 times 20 20 k ohm resistance, 20 times 10 to the power 3. Okay, and solve for this one, you will end up getting 0.22 voltage. So now we have the VGS minus VT, and we know the VT is provided in the question, that is 0.5 voltage, that's the threshold voltage. So from that one we can calculate the VGS here. VGS is equal to VGS minus VT is 0.22, and VGS, Alexa stop, VGS minus VT is the VDS in that region. So now we have the VDS as well. VDS is 0.22, and if we solve for VGS, that is going to be 0.22 plus 0.5, so 0.72. So this one actually helps us to find two things here, VGS and VDS right away. So VGS is 0.72 and VDS is 0.22. So in the B, we are interested in the point B. At this point B, VGS is the x-axis and VDS is the y-axis. So if we express this one, VDS is the y-axis, so that one comes secondly. So this is like B 0.72 comma 0.22. This is the coordinates. Okay, now we have done that, and the next part is asking what is the small signal voltage gain of this amplifier. Okay, to find out the voltage gain, small signal voltage gain, we use this equation. AV, that is voltage gain, that is equal to Kn times V over drive times the RD voltage, RD resistance, and the Kn is 10 milliampere per voltage square. That's provided in the question, so we plug that one here, 10 milliampere per voltage square, and then V over drive also given, that is 0.2. Put that one here, and then RD we calculated to be 20 k ohm resistance. Put that one also here, and if you solve for this one, you're going to end up getting minus 40. That's the gain. Okay, so that is, this one is what is the small signal voltage gain of the amplifier. We just found it out. Assuming linear operation, what is the maximum allowable negative signal swing at the output? Maximum allowable negative signal swing. To find the turnout, what you have to do is we had to look at the B region and the Q region, and the difference between the VDS in those region is the maximum allowable swing. So let's note that, and we just solved for the VDS at this B region is to be 0.22. VDS in the B region is 0.22, and VDS in the Q region is given in the question, I guess. Let me see. Yeah, it's 1 voltage, is point Q, 1 voltage. So the difference between is going to be the maximum allowable signal swing. So we can say, therefore, the maximum allowable negative signal swing at output is the difference between these two, that is 0.78 voltage. Okay, now we have this one. Let's see what else we have. We have one more thing, I guess. Okay, what is the corresponding peak input signal? Okay, to find out the peak input signal, but we know this AV also have another equation, that is AV is equal to output voltage over input voltage, VO over VN. So if you are interested in the peak input voltage, then rearrange this one in terms of input, that's AV over V output, and the gain we just calculated, that is 40, and the V output is the maximum allowable, that's 0.78. Put that one over here and solve for VN, that is 19.5 millivoltage. Okay, and that is the peak input signal. .5 millivoltage. Okay, and that's it for this video. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.